You ever seen a magic trick that seems to just defy the laws of physics? Well, today we're looking at the engineering version of that, an advanced RC helicopter that flies perfectly fine without a part that's considered absolutely essential. We're going to unravel how some really clever software can completely replace a critical piece of hardware.
So, how in the world do you get around what seems like a fundamental rule of helicopter mechanics? The secret, as we're about to find out, isn't in gears and bearings, it's all in the code.
Okay, so to really appreciate this little bit of software magic, we first have to understand the mechanical puzzle it's solving. Let's start with one key component you'll find in pretty much every helicopter out there. And that's a one-way bearing, also called a freewheel. Now, if you've ever ridden a bicycle, you know exactly what this is. It's the thing that lets you stop pedaling and just coast, right? The pedals don't keep spinning wildly. In a helicopter, that's not just a nice feature, it's a non-negotiable safety system. If the motor quits, the freewheel lets the blades keep spinning from the airflow, which lets the pilot glide or auto-rotate down to a safe landing. The helicopter we're looking at today, yeah, it just doesn't have one. Its main rotor is literally locked directly to the motor. And to make things even crazier, the tail rotor is driven by its own totally separate motor. This setup creates a huge challenge. I mean, think about it. If the motor is physically locked to the rotor, what on earth happens when you cut the power? So how does this thing even fly when the power is on? Well, it turns out there's this constant high-speed tug-of-war happening inside its flight controller. It's basically a battle between two opposing software goals. In one corner, you've got the governor. Think of it like cruise control for the rotor blades. Its only job, its entire reason for being, is to keep those blades spinning at a perfectly constant speed. Then, in the other corner, you have the yaw control system. This system's job is to control which way the helicopter's nose is pointing, and it does that using both the main motor's torque and the tail rotor. And here's where they fight. See, to turn the helicopter left, the system actually increases the load on the main motor. It uses the motor's natural twisting force, its torque, to swing the body around. But to turn right, it uses the tail motor. So you've got one system screaming, keep the motor speed steady, while the other one is constantly messing with the motor's load to steer the helicopter. The result is this incredible, delicate balancing act. The two systems are just locked in this perpetual tug-of-war, making thousands of tiny adjustments every single second just to keep the helicopter stable. And you've got to understand this constant battle because it's the key to everything that comes next. All right, now for the main event. This is where it gets really, really clever. How does the system handle gliding without power, auto-rotation, when it seems mechanically impossible? The answer is just an incredibly elegant software fix. The moment the pilot hits that throttle cut switch, a rapid sequence kicks off. First, the tail motor, which is now pretty useless, just shuts down. Then, and this is the crucial part, there's a handoff. Control of the main motor is transferred from the speed-obsessed governor over to the direction-obsessed yaw system. And this leads to the big mystery. As the blades are being spun by the airflow, the motor, still physically connected, acts like a generator, creating drag. That drag would slow the blades down and cause a crash. So how does the software know exactly how much power to feed the motor to perfectly cancel out that drag and create a virtual freewheel? The solution is this beautiful, self-regulating loop. Here's how it works. That motor drag creates a tiny bit of reverse torque, which starts to make the helicopter's nose drift. Well, the yaw gyro, a sensor that detects rotation, sees this drift instantly. It then tells the motor to apply just a tiny bit of power, just enough to counteract the drift. It keeps doing this over and over until the drift stops completely. And here's the real magic. The system doesn't need to be pre-programmed with some perfect zero torque value. The yaw control loop finds it all by itself. Its only job is to keep the nose straight, and the only way it can do that is by applying the exact amount of power needed to cancel out the motor's drag. It effectively creates a perfect virtual freewheel, just as a side effect of doing its main job. This is what makes the whole design so incredibly elegant. The software isn't calculating the answer, it's feeling for it. This existing PID loop, which is just a simple control algorithm, its only job is to keep the nose straight. And in doing so, it solves this incredibly complex auto-rotation problem, kind of by accident. It's just beautiful engineering. But the story isn't quite over. This unique logic has one more surprise in store, a totally counterintuitive consequence that shows up during high-speed flight, a phenomenon they call forced overspeed. So, let's set the scene. The helicopter is in a fast dive. Air is rushing up through the rotor, spinning it way, way faster than the governor's target speed. At the same time, the tail motor is at idle, but it's still producing just a tiny bit of a rightward push. Now, the logical question is, why doesn't the governor just use the motor as a brake to slow the rotor back down to its target speed? I mean, it seems like the obvious solution, right? And here's the brilliant reason why it can't. If the main motor were to brake, it would create a reverse torque. That reverse torque, combined with the small push from the idle tail motor, would send the helicopter into a violent, uncontrollable spin. The software understands this, so braking is absolutely 100% forbidden. See, yaw stability, keeping the nose straight, is the system's #1 absolute highest priority. It's more important than even maintaining the correct rotor speed, so the motor has no choice. It has to surrender to the aerodynamic forces. It effectively just lets go and allows the rotor to spin up freely with the airflow. And that brings us to this crucial takeaway. This forced overspeed isn't a bug, and it's not even an intended feature. It's a necessary consequence of the software prioritizing stability above all else. To keep the tail straight, the motor is simply forced to let the rotor run wild. So let's just recap this whole journey. We started with what seemed like an impossible mechanical problem, and we watched it get solved with some incredibly elegant code. We saw how simple control loops can create these amazing self-regulating behaviors. And finally, we learned how a strict set of priorities can lead to some really unexpected but perfectly logical outcomes. And that leaves us with one last fascinating question. This whole story was about replacing a single, simple mechanical bearing with software. It really makes you wonder, what other complex physical hardware problems are out there right now, just waiting for their own elegant solution, written in a few clever lines of code?